Greetings, guys. This is a lesson about graphing parabolas that are written in conic form. Conic form. So here we go. This is just going to be right to the point. I'm going to show you how to do this, and if you're a little bit confused, maybe let it play all the way to the end of this lesson and come back and rewatch it. At first, it's going to look a little bit foreign to you because you've never seen this, but it really is not the worst thing I've ever had to teach a kid. So here we go. First things first, we have two formulas to guide our thinking. One of the formulas has x squared in it. The other formula has y squared in it. And you'll notice there's this little 4p thing. Well, that's just part of the formula. But the big takeaway, the big idea here is when x is squared, over here it says when x is squared, the graph opens up or down. If it's positive, it's going to go up, negative, down. But here is something we have not done before. See, there is a potential where the y part is squared. When y is squared, we've never seen this before, but when that part's squared, the graph can go right if it's positive or left if it's negative. Now, there's one thing we need to do before we start the process, and that is make sure that the squared information is alone. Then it says set the coefficient equal to 4p and solve for p. So you're going, what does that mean? Also, it says we use p equals whatever we got to find our focus, and we use p equals to find our directrix. And you're like, what is that? Let me just go through, I'm going to go through 4 examples. You're going to see that it's really not as scary as it sounds. But we're going to start with one that opens to the right. Now, wait a minute. Here's the deal with this. What's squared? The y part is squared. We've never seen that before. We've only seen the x part squared. But when the y part is squared, you will notice that my number, this 8 right here, this 8 right here, well, guess what? That's my coefficient. That's what I mean by my coefficient. So I'm going to take that number 8, and I'm going to set it equal to 4p. And I am then going to divide by 4. Because I am solving for p. I want to know what p equals. What does p equal? It equals 2. 8 divided by 4 is 2. P equals 2. So see where it says in our notes here. We set the coefficient equal to 4p. Cha, I did that. And I solved for p. Now I know that. We use whatever p equals. So in this case, when I say p equals, well, in our case, we have p equals 2. We're going to use it to find what's called our focus. We're going to use it to find our directrix. So here we go. Those are definitions. Those are things we don't know. They're brand new words. Let me explain what they mean. So here we go. I'm going to graph this parabola. Before I do that, I need a coordinate system. So I'm going to give myself an x and a y. Oh, come on. Hang on a second. Let me try that again. See if it snaps straight. There you go. First off, origin is where the vertex is for all of these. So this dude right here, that's my vertex. My vertex for every single graph I'm going to draw is 0, 0. I am not moving these graphs around the coordinate system. Then, this 2, this p value that I found, well, you know what? I'm going to count 2 units to the right. And I'm going to mark that off, and I'm going to tell you right now, that thing right there is going to be called my focus. The name of the focus, it's just a dot. Where is that dot? Well, that dot's at 2 on the x and 0 on the y. I'm just naming it. It's a dot. It's a point on the x-axis. Well, what is that point important for? Well, here's the thing. You guys know this. If I want to graph a parabola, and I'm just going to sidetrack you just a little bit. I want to graph a parabola. I could go like this, yeah. But you know what? Some parabolas are skinnier. Some parabolas are wider. Heck, some parabolas open down. We can do all that kind of stuff like that. I'm going to erase all that junk. But the thing is in this method, in the method I'm using to show you how to graph this number here controls how wide my parabola is. My parabola is 8 units wide. Now, what if this number was a 10? Well, it's 10 units wide. What if that number was 20? It'd be 20 units wide. I'm starting with 8 because 8's nice and easy to count off. When I say count off, this is what I mean. We start at the focus, so I'm going to put my pen on the focus, and I'm going to go 1 unit, 2 unit, 3 unit, 4 units up. I'm going to go 1 unit, 2 unit, 3 unit, 4 units down. Here is where, oh crap, that was kind of wobbly. That's where my parabola is. My vertex is at the origin. This thing called the focus, well, it's just a point inside the parabola. We use it to count off how wide our parabola is. Now, this thing, I didn't tell you about this yet, but whatever that number is, that thing is called our focal diameter. That's what it's called. It's called the focal diameter. So the focal diameter is 8 units in this particular problem. Why? Well, if you were to count all the way from the top part where it intersects to the bottom, you'd count 8 units. So, what about this stuff here? Let's look back at these notes here. So it says, I made sure the squared info was alone. Did I do that? Yeah. At the beginning, the y was by itself. I set the coefficient equal to 4p. So the coefficient is that 8. I did solve for p. I got p equals 2. And then once I knew what p was, I found the focus. That's the dot inside the graph. The focus is important because that's where I count my focal diameter off from. And then you have to, you might say, what is this thing called a directrix? Now, this is the hard part for me because a directrix is a line that lies outside of our graph. And it is the exact opposite of the focus. The directrix would go 2 to the left. Why? I'm just telling you it does. That's its definition. The definition of the directrix is that it's a line that lies outside of our graph, and in this case, it's going to be a vertical line. So I'm going to draw it in a different color so it stands out on my page here. Oh crap, I missed my dash. Let me make that look a little better here. Oop. Oh boy, I'm going to undo that. I'm not going to try and make it look any better. You know what, I'm just going to put a big dot here so it looks like it went through there. All right, this guy right here, this guy is called the directrix. And do you notice that my directrix cuts through at x equal -2? So that's the name of our directrix. So take a look. Let's breathe in some of this goodness we have in this lesson. I'm going to use an orange highlighter. I've got an important dot called the focus. Focus is it's a dot, so I just name it. I'm not really concerned with asking you guys what the vertex is because it's going to be the same. It's going to be at the origin for all of these. But then I have something called a focal diameter. That's how wide my graph is, 8 units wide. And then I have this line outside called the directrix. Okay. Now, keep in mind, this is a very quick lesson in this. And this, if you were in class to get this lesson, I'd be able to answer your questions right now. But since you're watching this video at home, for either review purposes or maybe you missed class that day, well, you're going to have to just realize you can't ask me any questions since it's pre-recorded. So here we go. Let's look at this one. Oh my gosh, x squared equals -8y. So here's the deal with this. I am going to point this out to you a little bit smoother this time in order to answer the questions on the homework. they're going to ask you, what is the name of the focus? They're going to ask you, what is the focal diameter? They are going to ask you the name of the directrix. So the focus is going to be a point. So I'm going to know that when I get there, I'm going to have some point. The focal diameter is always going to be so many units. So I'm going to fill in this blank when I get to it. And then the directrix is always the name of a line. Now in the last problem, my directrix was a vertical line, but I'm going to tell you, in this one, my directrix is going to be a horizontal line. So my directrix this time is going to be a horizontal line, so it's going to be y equals some number. Now I'm going to fill in all these blanks as we go, but I know I'm going to graph. Oh, come on, that was really bad. There we go. Oh, much better. And here we go. I'm going to start with a yellow highlighter. Do you see that this is a x squared? If it's x squared and this number 8 is negative, it means my graph is going to go downward. So I'm just like, in my brain, it's going to go down because the vertex is right there. That's my vertex. And I'm going to say 4p equals negative 8. I'm going to divide by 4. So I'm doing very similar answer to last time. My p-value is negative 2, which means, hey, instead of going right or left, I'm not going to do that because that would only be if y was squared. I'm not going to go left. I'm not going to go right. I'm actually going to go up or down. And since this time I have a negative, I'm going to go down. How far, how wide, all that stuff has to do with this guy. So I'm going to go down 2. Negative 2 sounds like go down 2. Now I go, hey, you are called the focus. What is this guy's location on my graph? His location on my graph is at 0, negative 2. I went down 2 units, but I didn't go sideways. Also, my focal diameter, whatever this number is, whatever they gave me to start with, is going to be my focal diameter. But there's one little twist, and I didn't mention this at the beginning because it's very easy, and I didn't want to freak anybody out. But the focal diameter, since it is a positive value, it's got to be. You can't have a negative diameter of something. So the definition in our book, if you want to look it up, it says the focal diameter will always be the absolute value of whatever that coefficient is. So look, I'm just going to briefly go back to my first one. Whatever the coefficient is, in this case it was an 8, not a negative 8, but if I took an absolute value of 8, I'd still get 8. There's my 8 units wide. So when it comes to this, what is the absolute value of negative 8? It is regular 8. So its focal diameter is going to be equivalent to my first example. I'm going to go 1, 2, 3, 4 units sideways, 1, 2, 3, 4 units this way, and then there's my parabola. It opens downward. It has a focus at 0, negative 2. It has a focal diameter of 8 units. The directrix will be the opposite of the focus. This is always true. The directrix would be opposite of the focus. I'm going to use a different color. Go back to red for my directrix. And there he is. Or she is, or whatever. It's a directrix. And that name would be y equals, where's it crossing the y-axis? At 2. So we would call it y equals 2. That's my directrix. So there's 3 ingredients that we're always going to look for when we do this. A focus. Well, that is a dot inside of my parabola. Focal diameter, that is how wide the parabola is, and I have to count starting at the focus. Then the directrix is this weird line that lies completely outside of the parabola. Okay. Remember, I said if you have to, it might be easier just to watch this and then come back and rewatch it if you get stuck. But I'm trying to help you out in case you missed class or you wanted to get a little more lesson from me. Here we go. I'm going to look at, I have 2 more examples, but I want to do something I haven't done yet. I want to make this coefficient here. I want to give you a number that is not going to always be easy to solve for. But I'm not going to try and make you insane. So here's my next one. It says y squared equals negative 6x. So, once again, when I do my math, I am going to find a focus. I am going to calculate a focal diameter. I am. This is true. I am also going to name a directrix. I will end up with a graph. So here's my coordinate system. And my vertex will be at the origin for every single one of these. And my first question is the squared stuff alone? Remember, I'm going off the very same notes I did at the beginning. Is the squared stuff alone? Yes, it is. And then I say, who's squared? The y is. If the y is squared, and this guy over here is negative, it means my graph is going to open to the left. It does. That's what it means. Well, we haven't done this yet. That's true, we haven't. But this one's going left. So let's crunch some numbers. First things first, whatever that number is, whatever they gave us, we set it equal to 4p. We divide by 4. And then this is where we go, wait a minute, negative 6 divided by 4? I can't do that. Well, yeah, you can. You could reduce it. You could call it negative 3/2. Or if it makes your brain happier, call it negative 1.5. Or if it makes your brain even happier, call it negative 1.5. See, negative, let's say that's 1 unit. There's 2 units, so negative 1.5 would be right there. That's okay. You don't have to, make all your units, oh, I'm going to make every dash count as a half or something. Nah, just, there it is. It's between negative 1 and negative 2. Hey, what is the name of that location? Well, that thing is called the focus. And I would go left 1.5 units, and I would not go up or down. So my focal point, I'm just going to name it over here formally. Then, what's my focal diameter? Well, what number did they give me at the beginning? They gave me negative 6. I will take the absolute value of that, and then I will say unto you, the focal diameter is 6 units. Oh, so I'm going to have to count 1, 2, 3 units up, 1, 2, 3 units down for a grand total of 6 units. Gosh, I'm trying my best to draw, but I get wobbly when I... Okay, anyway. 6 units is my focal diameter. You can see it right here. 1, 2, 3, 4, 5, 6 total. 6 units. And then directrix. Well, the directrix is the exact opposite of the focus. So since my focus is at negative 1.5, my directrix will cross at regular 1.5. And that would mean my directrix would come down through here. Come on, straighten out. Okay, it's not going to straighten out. But you get my point. My directrix would be at x equals 1.5. That is done. We're done. What's my focus? I named it. What's my focal diameter? I measured it. What's my directrix? I marked it. It crossed the x-axis at 1.5. That's why we call vertical lines x equal. All right. Let us practice one more time. And remember, you can pause me, you can rewind me, you can go through this as many times as you want. If you're in class, you can ask me questions about it. Here we go, last one, because I didn't do one like this yet, but it's not as spooky as it looks. It really is not. But I got to tell you right now, this particular parabola is going to open down. How do you know that? Well, I know that the x squared piece is not by itself yet. The x squared is not by itself. So my first step is I got to get it by itself. So I'm going to move this over. I'm going to take it away, take it away, take it away now. That's gone. And I get 2x squareds equal negative 5y. And then I say, wait a minute, the squared thing is still not alone, so I have to divide by 2. And then I get x squared equals negative 5/2 y. And you might say to yourself, oh, crud. Okay, so the squared thing is finally alone. Yes, it is. It happens to be a squared x, and oh yeah, I see this is negative, so it must be a graph that opens down. Yep, that's what it's going to look like. But now I have this horrible number that I've set equal to 4p. Well, that's okay. It really isn't that bad of a thing. There's a couple different ways to look at this. I got to get p by itself, so I could divide both sides by 4. But just in case you forgot, dividing by 4 is the same as multiplying by the reciprocal. So I'm going to do it this way, because I can do it in my head then without grabbing a calculator. If I do 1/4 times 4p, those cancel. I get p. If I do this, it's 1 times negative 5, and 4 times 2, that's 8. So what does p equal? Negative 5/8. Oh, that sounds horrible. It's not the most wonderful thing I've ever had to work with in my life. No. But I know what 5/8 is. It's a little bit less than 1. That's what it is. So when I sketch this out, I'm going to tell you, to make your life easier on the assignments that you have to do here, and realize I'm not going to give you every single problem has a really ugly fraction in it, but here's what I'm going to show you that'll make your life a little easier. I know this graph is going to open down, so I'm going to make my coordinate system look a little bit different here, so it's a little bit less. And since my unit that I'm going to work with is negative 5/8, I'm just going to make like my dashes really big, like that's 1 unit. 2, because then I have some room to work with. Like here's 1 unit, 2 units, right? If I make my dashes bigger, then guess what? That's about negative 5/8 from the origin, right? Because there's my vertex, you know. I'm going to get rid of that because it's going to be in my way when I find my directrix. And then I say unto myself, what did I just put on the graph? I put the focus on the graph. I didn't go sideways. I went down 5/8 of a unit. Now I'm going to talk about the focal diameter, because this is where some people are going to cry a little bit. Well, the focal diameter means I'm going to take the absolute value of this guy right here. I totally am. Let me get these brackets out of the way, and I can go like this. Wham, bam. So my focal diameter is 5/8 units. That means half of my units go on this side, half of my units go on this side. You go, oh no, how do I take half of 5/8? You go, 1/2 times 5/8. Half of 5/8, what is that? It's 5/16. So I'm going to go 5/16 of the way over here. I'm going to go 5/16 of the way over here. And then I'm going to go vertex. I'm making sound effects. I don't know why. But look, if I go 5/16 of the way over here, and I go 5/16 of the way over here, 5/16 and 5/16 is 10/16, which reduces to 5/8. So there's my unit. Oh, that's right. And the thing is when you have a focal diameter that's tiny, you're going to have a skinny graph. It's going to make that thing look very skinny, that super tiny focal diameter. Once again, if you want to ask me about this lesson, you got to be in class to do it. But I am not lying to you. I haven't changed the process. I'm doing the exact same thing every single time. It's just the numbers sometimes get a little uglier. Now, I'm almost done. What's the last piece of the puzzle? Directrix. And when I want to find the directrix, well, I would go the opposite of the focus. So I'd go 5/8 up. And just like other parabolas we've drawn, the directrix this time would have to be a oh my god, that was really bad. Oh, but I made it look pretty. Horizontal line. It crosses the y-axis at 5/8, so we call it y equals 5/8 because it's horizontal. And that's all she wrote. That's it. So just a real quick recap of the notes. I'm going to scroll up to the top real quick. So if you ever feel like taking down notes or whatever on these videos, just pause me. Remember, you can pause me, you can rewind me. Here we go. I'm going to scroll back up to the top. So, remember, this is called the conic version of a parabola. There are two formulas. This guy is when it's going to open up or down. This guy is when it's going to open right or left. But we can't do anything unless the squared stuff is by itself to begin with. So my very last example, I had to do something to get it like that. Whatever that coefficient is, whether it's a pretty number or an ugly number, that coefficient, I set it equal to 4p, and I got to figure out what p is. Once I know what p is, I can find the focus, I can find the directrix, and the one thing I didn't mention here in the notes was focal diameter. But focal diameter is the absolute value of whatever they started me off with. Whatever they start me off with, I take its absolute value, I get the focal diameter. Sometimes that focal diameter is a nice pretty number like 8 or 6 or 4 or whatever. And then sometimes that focal diameter is an ugly number. Just remember, half of it goes on one side of the focus, half of it goes on the other. So how do you find half of the focal diameter? You multiply it by a half. Or if you want, multiply it by 0.5 if you're working in decimal. Okay, guys, that is the end of this little video for graphing a parabola using a conic version of it. Okie doke.